Okay, good morning. Hello, and we are going to have a webinar today. What is the monitoring and troubleshooting of artificial lift wells with Mr. Sergio Caicedo. He's going to prepare and give. He prepared for us a very important information. But first of all, I want to introduce our company. We are UPC Global. And who we are a leading consulting company that offers strategy solutions in the area of artificial lift and production optimization. We supply hardware and software and provide training oriented to analyze, optimize the well's performance. Our mission is to maintain trust among our employees and customers by providing advanced technical support in all equipment, service or training that we supply by having the ability to face the challenge, especially in these times, in these moments in the world, performing well in brands and solve any problems that always oriented to growth, to be transcendent by living a good way in all work we are assigned to do. We are specialists in artificial lift, and our vision is to become a leader provider, service, training, and consulting company in the artificial lift business segment, with different locations through the United States and around the world to offer different service and supports to our customers with the best quality and safety. Let me comment that we have about 20 years in oil industry with 4 bases in Latin America and also in the United States. And we have done business in more than 40 countries in the world and have exclusive representations in Latin America with brands like Ecometer. Our main services are field data acquisition, optimization, analysis, and elaboration of production plans. We have specialized trainings, and both in presential and online academy, and other services as telemetry and automation. And also we have mentors and specialized guidance in order to solve problems with wells. And let me introduce you Mr. Caicedo. He's a Master of Science and is a physics and computer engineer from Simón Bolívar University in Venezuela and have a Master of Science in Petroleum Engineering, with 26 years of experience as a specialist in artificial lift wells, productivity and software development applied to oil production. He has trained more than 700 engineers in oil production area in the different companies that he has worked. He has developed innovative projects and has worked as a specialist in artificial lift in Venezuela, Kuwait, the United Arab Emirates, and United States. He was awarded with the SPE Middle East Production and Operations Award in 2015 for his technical contributions in artificial lift to produce hydrocarbons. Thank you, Sergio, for being here today, and we are glad to have the opportunity to talk to you. People who just arrived to our webinar, during the presentation, you can write your questions or comments in the chat, and at the end of the presentation, we will answer all of them. Thank you, Sergio.
Okay. Welcome, everybody. We're going to have this talk about the monitoring and surveillance of artificial lift wells. So we're going to have a brief introduction. We're going to talk about monitoring and surveillance. We're going to talk about surface sensor, downhole measurement from surface, downhole measurements with downhole sensor, in pumping methods, calculation with measured values, troubleshooting, failure analysis, and real life, and finally conclusion and recommendations. So what is the main objective of the artificial lift engineer, the person in charge of this? And you are going to say optimize, but what does the optimize word mean? Optimize mathematically means to maximize the favorable things and minimize the unfavorable. This is from the mathematical point of view, and it's also very important because what is we are doing in the field, and we have to do this subject to constraints. So, what things we want to maximize? We want to maximize production, but also we want to extend the run life because we are making money. We want to maximize the net present value. And so all the positive things we want to maximize. And we want to minimize the things we don't want. We want to reduce the lifting costs. That means resources. I want to reduce the power electrical consumption in the pumping methods or reduction the gas injection in the gas lift methods. We want to make logistics easier, which will reduce the manpower, and people can in the field can use that time to do something else in the company. We want to reduce the deferred production. We want to minimize the operational issues. So all the positives in green, we want to maximize. All the negatives, we want to minimize. But it's not so easy because we have some constraints that we have to face in the field. For example, sometimes we have to take care in some cases because the surface facilities we have a maximum capacity for water, for example, and we have a power limitation. We don't have infinite power limitation when, for example, when we have generators, we have to distribute the power of the generator between those wells, and then the logistics capacity and so on. So that is the meaning of the word optimize. If you talk about optimize with a person from drilling, the meaning for them is completely different. But here, what I want to highlight is that we want to maximize the good things and minimize the bad things. That is but that means a lot of things. Sometimes we only think about production. That is valid, but please keep in mind that the definition can be extended for the better profit of the company. So to achieve this optimization goal, we need to monitor the wells, and a monitoring program can be manual or automated. It doesn't matter. What you have to do, you have to identify opportunities, detect anomalies in the lifting system or in the well or in the reservoir, quantify the performance of the lifting equipment, quantify the well or the reservoir performance, avoid operating on the unsuitable condition for the lifting system or for the well or the reservoir, because that will reduce the life of the artificial lift system or the life of the reservoir. We need to identify and correct failures. This list of activities and maybe some others you have to do in the field. It doesn't matter if it's automated or manual. This is the things you have to do to achieve the optimization goal, to increase the good things and reduce the bad things. So the surveillance program should do, if we have a system, manual automated, we have to monitor the artificial lift operations and the reservoir performance. We have to have fast operational actions. I mean, we have to see if we discover that we have to increase the speed, the pumping speed, or increase the injection gas rate, or shutting in a well, whatever. These actions have to be performed very, very fast. Okay? We have to determine the artificial lift run and off time, what we call the availability, the well availability. 90% of the time the well was producing, 10% was offline. Okay? We need to do that. We have to generate reports with key performance indicators, KPIs, and trend charts. That's important, of course. We have to store the artificial lift systems, the restaurant history. Sometimes it's not only you are going to find that only the information of the restaurant is there, the history, production history, but we need to know what was the sequence of the artificial methods and specification of those equipment that you have in the well. We have to sort of detailed description of the artificial lift system. This means? The design condition and expected operating parameters. So why is that? Because if I have when I arrive at well, and then I find an equipment, I need to know why this equipment is there. Is because it's the proper equipment, or maybe that was the equipment was available at that time, but it's not the best option, and so on. Then I need to know what are the expected operating parameters for that equipment and for the design condition and for the current conditions. Otherwise, I don't know. If I don't have that information, I'm not going to have idea if the well is behaving as expected or not. And we have to carry out statistics and failure predictions. Especially failure statistics and failure predictions are very important. We are going to talk about this later on. So when we acquire the data, it could be something is automated and something is manual. You are going to find the field that you are going to have a mixture of some values are online SCADA and some of them they are manual. And you try to make the manual as frequent as possible, and also the logistics is involved in this. For example, sometimes you have pressure and temperatures at the wellhead online, but the measurement, the production, water, oil, and gas, you have to measure in the test separator or in a tank, whatever. And you can do this once a month because you have too many wells to test and you only have one facility. Okay, so you have to live with this condition, and you need to know how frequent is each measurement that you are taking. So if the equipment is okay, after you do a troubleshooting, then you can optimize. It's possible if you have room to optimize. If the equipment operating with problems, you have to diagnose what is the problem. Then you try, it is possible to correct, maybe adjusting the velocity or changing the protection parameters in the automation system, or maybe you have to do a well intervention. We don't know. If the equipment is failed, then you have to select and design the artificial lift system that solves and make solutions to your situation. Pay attention that there is no opportunity or little room for optimization in a well with an unsuitable design or a failed equipment. If maybe it can run, but it's not having problems because of something failed. For example, in an ESP, one of the phases is grounded, so you know that your motor is not working properly, and you know that some stages are not working properly. They are wear by eroded by sand or whatever, or in gas valve, you know that the valve is not working properly, but then you need to change the valve or change the pump. Meanwhile, trying to optimize in that condition is very difficult, and that means you are losing production, which is one of the things that we want to increase, and we want to reduce the problems, as I mentioned before in the definition of optimization. Something important is the more variables and the higher the calculation frequency, then anomalies, problems, opportunities they are detected then uncertainty, because let me explain you this. If I only measuring the production or I measuring pressures once a month, and you measuring the first of each month, and suppose that the failure occurs next day, then after 29 days, you are going to discover that you have not been produced for almost 1 month, even though you thought that that your well was having availability, but it was in reality it wasn't. You thought it was working, but it is not working. So, but if I measure the production every week, or I measure something else online, then I can detect these problems very fast and take actions. We have to know what is anomaly is, that it's not behaving as expected, and then I have to know try to find what is the problem, or I can see clearly a problem, or it's working but I detect an opportunity. So probably the well is working, but I notice that there is room to increase production. But I need to detect this and take action fast. Second detail is the uncertainty of cost is reduced. The more variables I want to take, I can, with this, sometimes you have more than one possible problem that have the same symptoms. This is very similar when you go to the doctor. If the doctor, you go to the doctor and then you don't feel well, but the doctor does not take in pressure, temperature, blood test, or whatever, it's very difficult that to know what's happening with your health. The more exams it takes, then he can reduce the uncertainty. He can discard some problems, and then he can find what's the problem. That's the reason of having more variables. Then more situation can be the diagnosis. If I only take in temperature, it's not too much what I can diagnose, but if you take in pressure, temperature, power consumption, gas injection, including the design, more situation can be detected. Okay? The effect, the problem that you, or the opportunity, whatever, you can correct it, or you can take this chance very fast, because I know what is happening. I have better idea what is happening. Then the best corrective action can be better planned, because for example, you discover that your equipment, your pump is not working properly, it's out of range, whatever, then you find what was the reason of having this problem. But anyway, you have to, you take the decision to work over the well and change the equipment. But the question is, what system, what is the artificial lifting that you are going to install, and what is the design you are going to install? If I have a better knowledge of what is going on right now, I can do a better solution. I can plan better the next step in future, because knowing what happened in the past is important, but it's the easy part. The difficult part is foreseeing what is going to happen, the forecast, not only in the production, but also in the designs, and even if you plan to have more than one artificial lift in the future, I'm going to say, I'm going to use this system for 3 years, and then in the next 3 years, I'm going to change for another one. You can have a good planning. You can learn more about the problem, especially when you are doing tear downs, analyzing the failed equipment. You are going to learn what happened, what was the root cause, and so on. You are going to have more information. that to fill that all this gap, okay, you are going to have more accurate well models for simulating and designing your well. Which variables are being measured and where? Some of them are measured at surface, some of them are measured at bottom hole. The sampling frequency is online, like SCADA, daily, could be water samples at the wellhead, weekly could be fluid level, monthly could be the production, or annually could be a static reservoir pressure. And then you have to indicate what is, if this value is a direct and inferred measurement. Need to know, because sometimes you have a bottom hole fluid pressure because you have a downhole sensor, or sometimes you have a bottom hole pressure because you estimate from the surface with a correlation or with a fluid level with a commeter. Could be. So let's talk about the source of variable that you are those that you are measuring at the surface. That for those systems that use pumps, we are going to measure current, voltage, pump speed, torque, and on those gas lift, you are going to measure the gas that you are injecting, and even for all of them, sometimes you are injecting chemical. So I need to know how much are you injecting. That is, you measure that at the surface, and they are very important. Temperature at the wellhead, tubing and casing wellhead pressures, they are very important. Oil, water, gas rates at the separator. Water samples. There are, for example, some online water cuts. There are some devices that they can be calibrated to give you an idea of the water cut online. But they are very cheap. We can measure solid sensor at the wellhead. They are not quantitative, but they give you an idea of the qualitative. For example, they are microphones that they count the hits of the sand particles against the pipe walls, and of course we have what I didn't mention. We can have an online oil, water, and gas using a multi-phase flow measurement, but that is not a common practice because those equipment requires high rates because of the cost. So when you have a low production rate, you're not going to use this. Some anomalies can be detected from surface. I mean, anomaly is something out of my expectation. I expected to have a temperature at the wellhead of 130 Fahrenheit, and I'm having 90, or I'm having 200. This one, some of them, or with the casing pressure in a gas leak, I can have an idea something is happening with the valves. But sometimes you can say, well, some things could happen, or even if it's normal, then you have an idea, well, at least it doesn't look abnormal. So, but you cannot assure from those surface variables that everything is okay. At least you see, you can say, at least doesn't look abnormal, but you cannot have an idea of the following. For example, you don't know if you have ISP, if the internal motor temperature is okay, knowing the temperature at the surface. You don't have idea of that. You don't know about vibration in the downhole equipment because of the temperature or current is okay at the surface. We cannot infer those with these measurements I mentioned in this list. When you are injecting gas, you know that the volume is more or less what you expected, but you need to be sure that you are injected at the appropriate gas lift valve. So do not assume more than what you can really be sure, okay? Sometimes the only thing you have, because the downhole sensor you don't have installed or it failed. Not installed or failed, then the only thing you have is this at the surface, and you have to try to do your best with this, okay? For example, when the ESP, the current patterns, the behavior is fundamental for the ESP diagnosis of the well. There are some patterns that people, they are classified. Once that you see, you know what could be happening, having an idea. These are in the API standard. So when they tell you what could be happening, just paying attention to the patterns, not only the values, but also the shape of and behavior of the patterns, okay? In continuous and intermittent gas lift, the wellhead casing, injection and tuning, the production, the production and injection pressure at the wellhead. They give you an idea. For example, let me go back to the previous one, sorry. Here, this continuous current, it looks normal in behavior. The only thing that we have to check if the value of this current is what we are expecting from our design. Maybe it's stable, but maybe it's too low or too high. But then you see that here there are some spikes that you are not expecting, and maybe this is lightening, or maybe another well in the network that is starting. You don't know, but these spikes are not expected. Here we have what is a gas lock. You start the pump, and you are going to see that also when something happened with the current start going down, and so it also has this strange behavior. And here the current protection trips the well, starting again, and the same problem. Here you're going to see that these two, they look very similar, but here you don't see this strange behavior. You see a line that is going down until you reach too low current, but you don't see gas effect. The gassy well, this has some what we call some interference of gas, but not a gas lock. You have some gas, and you see that it is very similar. It's similar to the normal, but it has this small variation in the current. And the overload, you are going to see that the current start going up, and with no, it's not as smooth, but it's going up. And then here the protection, high current protection trips the well. The gas lift, the continuous gas lift, you're going to see constant pressure in the casing and a small variation, 10 psi in the tubing pressure. This is the normal. Here you're going to see something happening in the casing. You're going to see this is a valve opening and closing, and you're going to see the variation in the tubing is not irregular, is also with the same frequency here. This valve is creating problems here, opening and closing with a higher variation in pressure, opening and closing pressures. The same happens, and you see when the gas is increased, higher pressure, this valve starting not presenting so much variation, and you are going to see what happened with the casing, with the tubing pressure. That tells you a lot, the shape. Here, you're going to see what is, for example, when you are unloading a well, gas lift is a standard behavior. This is an intermittent gas lift well operating properly. So we need to know this, because if you're having a well that is supposed to be an intermittent gas lift well, and you see this continuous behavior, then you have a failure in your well. All the way around, if I have a continuous gas lift and I have this, then you have problems. And here you have something typical, is a very big hole in the casing in a continuous gas lift well, or even an intermittent gas lift with a hole in the tubing. This will be more or less the shape. It's very difficult, very different shape. We use this pressure chart, very important for gas lift. The patterns sometimes do not assure what is happening, but always tell you what is not happening. I mean, if you see this, say, I don't know what is happening, but it's not a steady state. Something is wrong here. You cannot tell me that this is working properly. Here you are going to see, I'm not sure where I'm injecting, but at least it's injecting in a steady state, and so on. So it's very important because you can discard states and conditions in the well and reduce the possible diagnosis in the well. In PCP, the measure of torque and current on the surface is used for rod protection. If the torque exceeds this quantity or the current is the same, because I know they are equivalent, because you know the motor and the wellhead in the PCP, and you know motor and current motor and torque, they are related. So the VSD, the variable speed driver, will give you what's the equivalent torque, and then you know what's the maximum torque that you will can handle. So you use this for protection. However, there are no classified current or torque patterns for diagnosis in the API standard for PCP. Probably some operators have their own PCP current torque patterns to do diagnosis, but they are not reported in the PCP standards. Okay. Then let's talk about measurement from the downhole from the surface. When downhole sensors are unavailable, the acoustic log, sonar log, or commonly known as echometer, use a gas gun, nitrogen CO2, and a surface microphone to determine the depth of the liquid level in the casing annulus from the surface. What I can get with the echometer gas gun, we can measure static fluid level in casing annulus or tubing. If your well has been shutting in for some time, then we can measure the liquid level, and that will be the static fluid level. We can measure the dynamic fluid level in casing annulus for pumping methods. For the gas lift, we can measure the casing annulus level just to check if the well was properly unloaded, but it's not going to tell you it is injecting from the where it's supposed to be. Estimate the static reservoir pressure. Estimate the pump intake pressure and the bottom hole flowing pressure. Estimate reservoir inflow performance, the well potential, and the current condition. Locate the approximate depth of holes in the tubing or casing. Gas flow rate through the casing annulus in gas lift well. In pumping methods. For gas lift, I can perform a check about the valves that are above the liquid level, okay? With a special, but I cannot see it when the well is flowing. I have to shut in the well, and I can give you an idea what's happening with those valves that are above the liquid level in the tubing and in the casing, in both. If the valves are a problem, or you have a hole below the liquid level, I cannot tell you, I cannot see it. Okay. So with the pumping method, what you are going to do, you are going to make a shot with the gun, a gas gun, in the pressurized with the CO2 or nitrogen through the annulus. Then you measure the time of this with the microphone, the traveling time, and then you can deduct, analyzing this pattern, Do you know what is the liquid level? Then you know what is the submergence. Submergence, how much liquid you have above the pump. We can use this. We can left this permanently in the well, so you can take a fluid level anytime from the office. We can estimate the intake pressure at the pump, and we can estimate the bottom hole at the perforations. We can use it for PCP, ESP, and soccer rod pumping. And we can check where are you injecting in the gas lift. We can double check. What is the advantage of this? That you are going to use this when you don't have downhole sensors. And the most important, you are not running anything you are not running any tool inside the well, so you don't have risk to get stuck with a fish with your tool. So that is very good. Also, with we can measure in the for soccer pumping, pin pumping, we can measure the dynamo cards at the surface, and with this, we can have a very good idea what's happening in the downhole pump with this measurement and some math using the wave equation that describes the dynamic of the road. We can do this from surface using what we call a horseshoe cell or a polished road transducer. Any of these two, we can measure the force that you are applying in the polished rod at any time. With this, we can get what we call the dyna cards, and with this, there are some patterns well defined and have been studied for many years. Then you can do a very good diagnosis of what's happening in your pump. Artificial intelligence is an excellent tool for pattern recognition for all artificial lift systems. For this kind of thing that to recognize a pattern, artificial intelligence is very good. Okay, I'm going to tell you where something else, artificial intelligence, can be used in artificial lift systems. When I have sensors downhole, they are very common in ESP, and what we call PCP. ESP is a PCP with a downhole motor. Okay, they are very common because they use the same power cable for data transmission, and the additional cost is small compared with the completion. I mean, ESP completion could be with work cover could be $300,000, and having the sensor is going to add you $20,000 additional. So, and you are going to see very important variables to extend the run life of the system. So that's why they're very common nowadays. Not so common with other methods like soccer rod pumping, PCP with surface motors, gas lift, jet pump, or whatever. They are not common because you are going to require an additional cable to transmit the data, and the cost is not so small compared with the completion. Maybe the sensor and the completion, the sensor is $20,000, and the completion for a PCP is $80,000. And then it's a very important. So people, for me, you should always run this, because if you use the data properly, then you can extend the run life, and that's going to add a lot of value for the company. The net present value is going to increase, even you are spending more in data. But it's important that you install and you use the information that you're getting this. Sometimes managers, they don't want it because they just having another graph in the report, but you are not getting more information, you are not using it. And if you are not using the information to very good, to have an idea about the reservoir, the artificial lift system, to extend the life of the well, then I understand that people, they don't want to use it. But when you use the information, then you are going to see that is the best investment you can have. Okay, let's talk about the pressure sensors downhole. You have the pump intake pressure. You use this to protect the pump against the pump-off condition. By the way, you need to have this together for the pump-off condition together with the surface casing pressure. If you have, for example, your pump intake pressure is 1,000 psi, and you think that you have liquid above the pump, take care, because if you wellhead pressure, your casing will the casing gas pressure in the annulus is 1,000 psi. That means that you have no liquid above the pump. So the pump intake pressure, together with the casing head pressure, is used to protect against the pump-off condition that is going to damage whatever pump you have there. And also to know where is your low fluid level, your dynamic fluid level. You are going to protect it against this. The pump discharge pressure, you are going to protect your system against the sulfate safety valve that has been closed and you don't notice, or someone accidentally closed the well at the wellhead, tubing clogged, viscous oil plug. Also, you are going to use this to multi-phase flow correlation, selection, and tuning. That is to predict better your well performance. And you are going to have the differential pressure, discharge pressure minus the intake pressure, to check about burst pressure, which is very easy in big diameter pumps in ESP, and pressure load on the pump for PCP and ESP. You need to know if you are loading too much the pressure. You can have very high discharge pressure, 5,000 psi, but if your intake pressure is 4,900, the differential is very low, so the pump is not being loaded with the differential pressure. Okay, so you have to be smart in this. Temperature only for ESP. You have the motor winding temperature. This is very important. This is only for ESP, PCP. You are going to use this, the temperature of the motor. It is an indicator of low flow. You are not cooling down the motor. It's also an indicator of high load in the motor and any phenomenon that hits the motor. For example, scales, carbonate, scale, and low motor efficiency that hit up the motor. The intake temperature is an indicator of recirculation. So maybe you have a hole in some place and you are recirculating, or something, because when you pass through the pump in ESP, especially when you have too many stages, due to the friction, you are hitting the fluid when it's passing through the pump. So the intake temperature high could be an indicator of this. And together with the motor winding, if you have high temperature in intake but low temperature in the motor, that means that the fluid is cooling down properly. But if you have high intake pressure and you have high winding, then the interpretation is different. It's not easy. Vibration and current leakage for ESP or ESPCP, whatever. The vibration measures or indicates mechanical damage. Could be high solids production, sand, or any other solid, we can have mechanical wear, and we can have resonance frequency. You're operating a frequency that is not good for your pump. There are some devices that measure current leakage. The current leakage is a measurement of electrical degradation of the system. Could be you are very close to a face to ground, or loss of insulation. It's not, has not been failed, but is starting to have this problem. We have to measure in pumping method the free gas. The free gas have some effects. First of all, the gas uses space. Okay, for example, if you need to produce 2,000 barrels and you're having 50% of free gas, that means that the pump capacity should be 400 barrels, 4,000 barrels, because 50% is gas. So 2,000 of those are liquid. Regardless of ESP, PCP, the gas is used in your space. Okay. Each method has its free gas handling limit and different effects. The ESP, sorry, not BS in Spanish, that is ESP. ESP, radial flow impeller, 10%. The ESP, but you are using a radial impeller that is 10% of limit. Once that you reach the 10%, you are going to have a problem with this. Let me check this. ESP. Sorry about this. Let me check it. Okay. If you have a mixed flow impeller, the limit is higher, 20. You have a gas handler, which is not a gas separator, something else. Then the limit is 40. If you have an axial flow impeller, the limit is 70. Most of the pumps, the most common are the radial and the mixed. These are not common, but there are some wells that they install, but they are not common. What happens when you exceed this limit? If you have then you have a gas lock. Once that you have a gas lock, there are two options. Or you treat the well from off the pump. If you don't do it and you keep going with a gas lock, you are going to overheat the motor. You are going to damage the pump, the completion. So you need to know what are the limits. For PCP, then the problem so the problem is going to be that you are going to overheat the elastomer and the reduction of roll life. There is a special PCP that's called hydraulic regulated PCP that can handle up to 60. Once that you reach that limit, you are going to overheat the elastomer and you are going to reduce the roll life of that net. In socket rod pumping, you are going to affect the compression ratio. You are going to have rod buckling. You are going to have a temporal gas lock, a low efficiency. Okay. In jet, the products are going to require higher volumes and pressure of a power fluid. So the free gas is the gas that is passing inside the pump. You have the gas through the annulus, but the yellow bubbles that passing through to the pump, that is the problem you are going to have. The equation is very complex, but the most important you have to know is that depends on the pump intake pressure, temperature of the intake, bubble pump pressure, solution gas, percentage of water, and separation efficiency, downhole gas separation efficiency. You need to know properly the PVT of your oil. You need to know very good how is the downhole gas separation, and the separation efficiency changes with each method. So you need to know this. The result of the equation have to be compared with your limit. So I need to use that equation and then see what is the limit. So just to show you, it's not so simple. If you pressure intake is above the bubble point pressure, that means that you have zero gas because there is no bubbles. Regardless of the GOR, even with 3,000 you have zero. In this case, you are in this area you are above the bubble point, so there is no gas because the intake pressure is very high. If the water increase, the numbers decreases. So it's not the same to have, for example, 3,000 of UR with 400 PIP, that is 96 of free gas with no separation. With 95% and 55% of free gas. So the equation, this is an example of the equation for the different cases. So water helps, and of course separation helps. Pay attention that here at the top is zero separation, and here 80%. So having here 80% of free gas without separation, and I have 80%, it doesn't mean zero. Still you have remaining gas, but still you have a lot. So we need to use the numbers. When you have for a fixed intake pressure, the higher that you are, the higher the free gas, but it's only one parameter, okay? Pay attention about the intake pressure. 3,000, you are 3,000 with an intake pressure of 2,400 has 70%, but a GR of 450 with a 400 PSI intake pressure has 75. So take care, because sometimes low GR, but very low intake pressure creates a lot of free gas. Okay? So not only the GR is the pressure you are having at the intake of the pump. Here I'm showing in colors to visualize this. What you have here is what would happen at different rates with pumps at different depths. The continuous line, the pump is at 10,000 feet. The yellow line, the pump is at 9,000. The red is at 8,000. The green is at 7,000. The blue is at 6,000. And here I have one is at 11,000 below perforation. The perforation is at 10,000, and you are going to see what happened. Black points mean less than 0 to 1% of free gas, essentially no gas. This blue is 5 to 10, red is 40%, and so on. Okay, so the position of your pump, which you know, I need to know where's your pump, and the intake pressure will tell you what is your free gas. So we can use the intake pressure to be sure how much gas you are having in your pump. So this is a smart way to use your data to know how is the situation at the pump in terms of free gas. When I combine the measurements with equipment specification, I got even more information. Direct measurements are usually used for alarms only, very low, very high current, very low, very high inlet pressure, and so on, compared with a fixed value for each well, which is a problem because someone had to pick that setting value, okay? More information can be obtained when using a specification of this equipment. Product specification, motor specification, installation report, expected design and operation values. Some indicators have a certain accuracy, or have more errors, but shows a clear trend. We can monitor the pump performance, we can monitor the reservoir performance online. Measurement with equipment specification is better than artificial intelligence. Believe me, do not try. When you have a well-known equation or something, I do not recommend to use artificial intelligence, because artificial intelligence, you need a bunch of data to train the network, the network, the neural network, I mean. And you are not going to know why it's taking a decision. If you don't have good training, then the intelligence is not going to be so smart. So use this for patterns. Do not use this for equations that you have a model. We need to know when to use equation and when to use artificial intelligence. I'm going to show you an ESP online flow estimation. If I have intake and discharge pressure sensors, this measure can be used to calculate online oil, water at the downhole condition, and then I can, from downhole conditions, I can take it to surface condition. The idea is to use the pump performance cost as a virtual meter. It's necessary to know the model of the stage and the number of stages installed. It allows production online monitoring as well as quality control for validation of production tests. Allows to check if the bottom hole flow is the pump, if the pump is in range, which is important to extend the run life. Here I'm going to show you in red, these are real data. Pay attention to the dates. I calibrate only once, and I could estimate the rate for 1 year, just as a reference, the reported liquid rate versus the estimated. And you can see that they are very good estimate, very, very good. There is a paper for this, for those that want to read. So I use the report flows as a reference. Only one calibration pump was used. Okay, that is this one in the here. Okay. PCP online flow estimation. When having intake pressure and discharge pressure with PCP, then a similar ESP flow estimation can be applied, but the difficulty is that the performance specifications Q versus delta P change fast and drastically with the swelling of the elastomer. I mean, in matter of 2 weeks, 1 month, you have a different pump, even it's still new, because the elastomer swells with temperature. Okay, so even when you have a friend of mine, remember he told me he had one store in Venezuela, a very hot place, and the starter almost stuck because of the high temperature. It was in the sun. In the afternoon, in the evening, when the temperature decreased, he could pull the water easily, but not when it was hot. So it swells a lot. BP. So when I use the curve of in the PCP of the manufacturer's curves, they are not reliable because they are for water and for some temperature. So that's the problem for the PCP. I need to do a calibration and do some additional math. PP online flow estimation. In wells with deep pumping, the effective stroke and pump fillage obtained from the downhole dynamometric card is possible to calculate the flow displays at bottom hole condition. With low cells permanently installed, you can have an estimation flow online. Of course, we have to do some additional corrections. For example, I know how much is apparently gas, and I need to know how much gas is flowing through casing. So I compute how much gas is flowing through casing with the fluid level shot, what we call the mini build-up, and we can compute how much gas is passing through the pump. But that gas is at downhole conditions. I mean, if your pump is replacing, due to the stroke and diameter, 500 barrels, and you have 50% of fillage, that means 250 is liquid and 250 barrels at pump intake condition is gas. So you have to change those barrels of gas at pump intake condition. Suppose that you intake pressure is 500 psi, then you have to transfer this at standard condition, that is 14.7 psi at 60 Fahrenheit. Then you have an estimation of the gas that passed in the tubing, and in the other side, you measure directly the gas that travels in the casing. Reservoir evaluation. If a pressure sensor is available at the pump intake or a sensor at the sand phase, the following can be evaluated. Static pressure, flowing pressure, with this additional calculation if the pump is not installed at the sand phase. If the distance between the pump and sand is 500 feet, you need to do a multi-phase correlation to estimate at the bottom. Then we can have the reservoir inflow curve. We can perform build-up, drawdown tests for permeability and damage determination. Once the well production estimated, I can remember I told you I can estimate online if I have an ASP with the sensors. Then I can know what is happening with the inflow online. So I can have this curve, and you know if you are producing a very high percentage of your absolute open flow, or you are producing a little bit of your reservoir capacity. That's why I tell you that is a part of the reservoir evaluation. And also, as I told you, you can measure. You know what should be the maximum production, the productivity index, that is the slope here in the flat part, and you can compare what I'm expecting with non-skin damage and so on, or after an stimulation. Equipment condition and evaluation. Detecting the problem requires that you monitor the well, requires additional information, design condition and operating condition, expected values. I'm expecting to, in this CSP, that the current is 60 amperes and I'm having 80 or I'm having 30, then it's not in the range and something is happening. Diagnosis is not simple because you can have for every simple, there are possible causes. It's not only one. That's the problem that the doctor had when you arrive. There are many reasons you can have a stomachache and need to know what are the possible reasons. And diagnosis is not simple because there are problems that are easy to identify and easy to fix. There are problems easy to identify and difficult to fix. There are problems difficult to identify and easy to fix. There are problems difficult to identify and difficult to fix. So diagnosis is not, and troubleshooting is not an easy thing. Inspection and maintenance. In production wells with artificial lift, it's only possible visual inspection and preventive maintenance in surface equipment, PCP, soccer rod pumping, I can do something in the unit, and so on. But other systems, especially ESP, then at surface I have DSD, valves, wellhead, but downhole I have motor, seal, separator, pump, cable, tubing. In beam pumping, I have DSD and beam unit at the surface. Downhole, the rolls, the pump, the tubing. PCP is the same, the beam pumping. In gas lift, at the surface I have compression line valves, control valves, injection valves. At the downhole, I have mandrels, gas lift valve, tubing, packers. In jet pump, the triplex pump, the separator skid is at the surface. Downhole, I have the jet pump, the tubing, and the packer. So I can, for downhole equipment, for the visual inspection, I need to do a work order, and that is the difficult part of artificial lift. The downhole equipment, you cannot perform a visual inspection. You can do it after you pull the equipment from the well in the workshop. You can do a visual inspection, but not when while working. Okay. Then failure analysis and run life. What are the factors that make the run life shorter? Downhole temperature, motor, cable, and summers, fluid level in the pump, the intake pressure, number of trip interruptions. When you have an ESP and you are doing many interruptions, the seal, the shaft, the peak stress in the shaft, the rods, that create problems, and you are going to reduce the run life. Installation quality, cable, joints, penetrators, etc. Operating practices, if you are pumping out of the range of the ESP, if you are overloading or underloading the motor or the cable or the surface unit, you are overloading the torque, you are creating problems. Design practices, what are the safety factor? How was the selection of the method? Is the right method? The equipment size, sizing, and materials. That is very important. Motor overload, sand, scale, asphaltines, improper configurations, corrosion, CO2, H2S. These variables must be monitored to infer the probability of failure. Then, learning from the failures. That is also part of this. Run life statistics, mean time to failure report, and predictions. I highlight in red prediction. Report is the past. Everybody knows that the pump in well A failed, yes, but I need to know why, what happened, what was the root cause, and so on. And I need to do predictions. Those wells that are not failed, they are not failed. And what's the prediction? They are going to fail. What's the probability of failure of that equipment in the next 3 months or in the next year? I need to do that prediction. What is difficult in lotteries and horse racing is not the report. You are going to read that in the newspaper. What is difficult is the prediction. If you predict well, and you can do it also in Wall Street, you're going to be rich. What is difficult is the prediction. That is the clue. Is it rational to do the same thing over and over and again and expect different results? If you are not learning and you're not changing, you are not analyzing, you are a problem. Corrective action in well operating with problems, improve operating condition, simple corrective actions on the surface. Sometimes you notice, oh, I'm running just a little bit out of the range of the pump. Let me reduce the speed. I'm going to be okay. Or the motor is overloaded or underloaded. In the ESP, I can downgrade the motor, changing the voltage and so on. Corrective action on failed wells. I analyze, I do the analysis of the failure, and then I learn about that method, and then I think that is then what is the best method, the best way to select, and the best way to design. Therefore, if we continue to collect failure reports without taking any corrective action, we will take the wrong life for the condition and practice in the field. If we continue to do it, you are going to have the same. The idea in time is that you are going to extend the wrong life when you are learning, and it's part of the monitoring and troubleshooting the wells. To improve practices, we need to perform root cause analysis to prevent from happening again, which is different of the failed item. The motor failed, but when you perform the root cause analysis, then you could find it was a problem of the design because the data used was not properly, had some errors. But then, or maybe the root cause analysis says raw material selection and so on. We need to know what was the root cause of this. There are an industry standard for root cause analysis for PCP and ESP. Okay. We have to use mean time to failure with Bayesian statistics, which means statistics with condition. It's not the same to say the run life in this field is 2 years, that to know the run life of this well having an overload motor, which is only in this well, the other wells are properly designed. That is something different. Big data, artificial intelligence provide better predictions for these kind of things. Okay. Conclusion recommendation: proper monitoring of well with artificial lift is extremely important as the run life and the performance affected by an inappropriate operation. ESP monitoring is even more relevant because it's an expensive equipment which is very susceptible to damage due to poor operation design, besides of the high production deferral associated. Understanding system monitoring variables, the purpose, the interpretation, and scope is critical for the artificial lift evaluation to ensure proper operation. Deep understanding of artificial lift system equipment and working principles are essential for proper monitoring. I cannot go and just taking data. One guy, if the guy does not understand the system, is essential. Surveillance was much more than acquiring values and a dashboard with alarms. Well, thanks for your time. If you have any questions. Can you hear me? Merlimar?
Hi, Sergio. This is Gustavo. I don't think Merlimar is on the line, but I can see one question or comment in the chat. I don't know if she's back. Merlimar, we can't hear you. I can see your email or your text on the chat, but we cannot hear you.
I can read the question here.
If you go to the chat, that'll be
Yes,
there.
I'm reading here. Pressure build-up measurements and production bottom measurement can be done from surface using continuous fluid level measurement in order to have a downhole test. Yeah, what happened is, remember the following. That is true, but remember that first, there is some uncertainty and errors in the measurement. It's more accurate at downhole sensor because maybe you have the downhole when you have your fluid level and the pump is far from the perforations. Then you have to, what you are going to measure directly is the fluid level. Then the pressure to the downhole needs some correlation and that have some errors. Second is in the case of ESP, downhole motors, remember that you are going to usually, by sure you are going to install temperature of the winding inside the motor because you want to protect the motor. The extra price for the downhole pressure is not too much. So once that you are going to install those temperature because you want to protect the motor, you want to check how is the integrity of the electrical system, then adding an additional downhole motor is not going to be much more expensive. So you are going to do it. Second, when you have downhole sensor and you have a fluid level, then you can even tune more the correlation that you are going to use with the committer. Then you are going to find in your wells maybe, okay, in my well I have found that we have to correct deducting 2%, 5% the estimation that the committer is providing. Okay, so it's not always that you don't need it. Always you need it. The more you have, the better. Okay, so I'm feeling. Currently, most of the wells with the SP use downhole sensor, but are the production companies with information they will common parameter. The problem I mentioned this is not only that you are going to acquire the data. What are you going to do with this data? So the problem is that sometimes people, they don't see any additional value because they are not doing too much with the data. As I show you here in one slide, I would like to know, let's think about this chart, okay? I'm showing here the values of those days that I have the pressure, the production measured in the test separator, okay? But I can have it online. I didn't do it, but I can have it online. So the problem is, you are going to tell me what is the value for you of having your production online without making a test separation test. Okay, so you are going to know what's really your production, which is very useful because you are going to see which wells are producing. It's very difficult when you have all your wells working and your production decreases, then you are trying to find where the production loss is. There are some easy cases that you are going to find that the pump is off, it's not working. That's simple. When the pump is working and you have low production, that is not easy to find where is the loss. Then having online production estimation is a very good use of these measurements. So they are a value. But if you are not doing anything and you're not estimating rates or something doing, just having a display of the pressure, I understand that some people, they don't see the added value. Any other question about those are the one I'm reading here. Let me see. Let me see. Excellent. Any additional question? Chat.
No, Merlimar, we can't hear you.
No, we can't hear you. Trying to find, I don't see any other question over here.
Well, Sergio, I think you will have to wrap up by yourself this time. Merlimar is putting some, guys, if you go to the chat, Merlimar is placing some links in there where you have access to technical information on the website. And
Yes, exactly. Merlimar is having a link with technical papers. You can visit our blog. You can visit the academy that has online courses 24/7 for the gas lift, nodal, and have some ecometer courses online. So you are welcome to see it. And here is our emails. You have any question for you? Any other question?
I think that's it, Sergio. I don't see any other question in the chat. And if you, the Merlimar is also posting an email, sales@opcoglobal.com. So if you want to reach anybody there, that'll be a good email to get in contact with UPC. And
yeah,
thank you, Sergio, for the presentation. I think that will be it for today. Thank you very much.
Okay. Well, I wish you to have a very nice day. Keep in touch, and I hope you have enjoyed this webinar and find it interesting.
Thank you. Bye-bye. See you next time.